Hello together and welcome to a new tutorial by EngineerDo. In this video I want to show you how easy and fast it can be to do your own discrete element simulation with an open source software. At the end of this tutorial you will be able to simulate the filling and unloading process for each type of silo like you can see here. This tutorial will include all necessary steps, starting with the generation of a simulation-friendly CD model, understanding of the simulation script, and finally the post-processing of the simulation results. If you like that video, please give a like and visit us under engineerdo.com. You will find a link to the website under this video. On the website you will find further explanation about this tutorial and a download section. There you can get all files used in this video. If you have any questions and critics, please leave us a comment. Here you can see a common workflow to set up your simulation. First we will design the CD model. For this you need a CD program which can generate STL files. In this tutorial I will use SolidWorks, but you can also use any free CD program like Autodesk Fusion 360. To write the scripts for Liggghts we need a text editor like Notepad. Furthermore, you need an installed version of Liggghts. While I will use a Windows compiled Liggghts version, the workflow does not change if you are working on a Linux computer. You will find a link to how to install Liggghts on Linux in the description. For the final post-processing we will use the open source software Paraview. Before we start with the CD model, let's have a quick look on what we want to model. Here you can see the dimensions of the geometry. We want to model a silo with a main diameter of 1.5 meters and a height of nearby 5 meters. The lower part of the silo is a conical. The dropping distance between the outlet and the ground should be about 1.5 meters. The ground should be a 5 by 5 meter square. Okay, let's go to the CD program. We open SolidWorks and create a new part. We will build all geometries as one part. This is very common for simple projects. First we draw the ground. Check the Z direction to be normal to the ground plane. Then draw a square and use dimensions of 5000 by 5000 millimeters. Check the center of the square is in the origin and click on Fix in the left menu. We close the drawing and extrude it in the negative Z direction. Set the thickness to be 10 mm. Now we change to the top plane and draw a half cross section of the silo. First we insert a construction line in the middle coming from the origin. Then we just draw the rough outlines of the silo and add the final dimensions by the Smart Dimensions tool. Now we use the offset command to get a wall thickness of 10 mm again. Finally, we have to close the gap between the two outlines by adding two further lines. Now we close the drawing and use the revolved base feature to get our silo in 3D. Next we add the frame. We look normal to the ground and draw two circles with a radius of 100 mm. Now we set the distance to the origin to 860. We know the radius of the silo is 750 mm, the wall thickness is 10 mm and the radius of the frame is 100 mm. Hence, the frame will contact the silo on the outer wall. Now we extrude the circles to the upper edge of the silo. Here it is important not to merge the elements, because this can result in a bad meshing later. Last we design an insertion geometry. This geometry will be later used for the generation of the particles in the simulation. We select the upper ring of our silo and draw a circle that is a little bit smaller than our silo. Next we extrude it like shown before. Now we have all elements we need. For the simulation, we must save each element separately as STL file. We start with the ground. Click on the ground and it will be marked blue. Then click to File, Save As, Data Type and select STL. Check you are in the right folder. Then we name it ground and check the options. Check that the output is on ASCII, the resolution on coarse, and the boxes are checked like you can see here. Press OK and save. You can see in the background how the STL model will look like. Click Yes and choose selected faces and click OK. Now we hide the ground and go on with the frame. Click on both frame parts holding Shift and repeat the saving. Click File, Save As, choose STL, double check the setting and save as frame. Now we select the insertion phase and repeat the saving. This time we will choose a fine resolution in the options to get a more accurate mesh and save it. For the inside of the silo, we select the upper and the lower part holding Shift without selection of the bottom. Now repeat the procedure a last time for the bottom and save it as lid. Finally, we save the CD file just in case we want to reuse it later. Close the program and switch to the folder where you save the files. Here we must change the ending. Like you see, the files are ending on .stl using capital letters. For the simulation, we just change it to small letters so Liggghts will recognize these files are STLs during loading. Here you can see the header of our script. The atom style granular defines that we want to simulate particles. The boundary FFF means that the boundaries of our simulation box are fixed. All particles leaving the boundaries will be deleted. Also, we are using SI units. The next two commands, communicate and Newton, we treat as default because these are just important if you use multi-cores. Here we define our systems variables. First, we define the boundaries of our simulation box. Here you can see how variables are defined. We use the keyword variable, then a random name, here xmin and xmax, followed by the keyword equal. After this, we write the value we want to use. In our example, the ground square lengths are 5 meters. We define the limit in x and y direction a little bit larger, so the ground STL will fit in. Here you can see that we will use the same coordinates like in the CD program. The origin is in the center of the square. In the Z direction, the silo has a height of about 4.5 meters. On top of the silo, we will generate the particles through the insertion phase, so we add an extra 0.5 meters. The second system variable is the time step. The time step defines the time that is represented by one iteration step. In our case, we use 1e-4, so each step represents 0.1 milliseconds. The suitable selection of the time step is often discussed in DEM. If you'd like to know more about this topic, leave us a comment. Now we go to the specific variables we want to use for our simulation. First, we define how many different materials exist. We set n atoms to 2. The first atom type is the particle material and the second one will represent our geometry material. We assume all geometries are made by the same kind of a material. We set the values for the Young modulus for material 1 and 2 to 1e8 and the values of the Poisson ratio for both materials to 0.3. Next, we define the contact properties. The first one is the coefficient of restitution. By the designation, you can see the difference to the material properties. The core 1,1 is the coefficient of restitution if two particles of type 1 are in contact. The core 1,2 is the coefficient of restitution if one particle, type 1, is in contact with our geometry, type 2. The core 2,1 must have the same value as core 1,2. The core 2,2 is for the contact of geometries. Hence, geometry contacts are not considered in Liggghts. You could also set it to 0. Now we follow the same procedure for the definition of our sliding friction values between particles and between particles and geometries. Same we do for the rolling friction values. Now we define our variables for the particle size and distribution. We define the number of different radii to 2. The first radius of the particles is 0.02 meters and the second one is 0.03 meters. The variable frag1 and frag2 means we want to use 20% of particles with radius 1 and 80% of particles with radius 2. The density variable we set to 4000 kg per cubic meter. In the next steps, we define the durations for the stages of our simulation and the filling conditions. We define the time to fill the silo to 5 seconds. We want to fill in a total mass of 5000 kg. Using these two values, we can calculate the filling mass rate. Here you can see how to use variables which has been defined before. To use the variable, you write $, curly bracket open, variable name, curly bracket close. Because Liggghts is using the number of iteration steps instead of time values, we have to transform our filling time to filling steps by dividing time by the time step defined before. After the filling, we want to wait 1 second until the particles are settled. Hence, we define a settle time and transform to settle steps like shown before. For the opening of the lid, we will define a variable for the opening velocity and set it to 0.4 meters per second. The open time we set to 1 second. The lid will move 0.4 meters in 1 second, which is the diameter of our silo outlet. Last, we define the variable for the discharge time and set it to 25 seconds. Transform it to discharge steps. Now we have defined all variables and jump to the next part of the simulation script where we will use them. First, we define a region with the keyword region followed by the name reg and the shape keyword block. Afterwards, we use our variables for the boundaries and add the keywords units box. Now we use the create box command to create a simulation box including 2 atom types for particles and walls and using the dimensions of the region reg above. The neighbor and the name modify command you can use as default here. Next, we define the contact model. We will use a Hertz tangential model and an EPSD2 rolling friction model, which are quite common. Using the time step keyword, we set the time step to our predefined variable dt. We use the default integrator for spheres. By the following fixed gravi, we will set the gravity value to 9.81 meters per square second and the direction of the gravity to the negative z direction. Now we define the material and contact properties using our variables. You can see that the material properties use the keyword per atom type, while the contact properties use the keyword per atom type pair, followed by the number of atom types and the value of variables. Here we load our geometries. We use the keyword fix followed by the name we want to use for the mesh, like silo followed by the keyword all meshed surface. To load the STL from a file, we type the keyword filed followed by the name of our STL file. We set the type to 2 for all walls. Now we have to downscale our geometries by a factor of 0.001 because we exported the STL files from the CAD program in millimeters, but in Liggghts we will use meters instead. After loading all geometry files, we activate these in the simulation by the fig walls command line. We will use the same contact models for the particle geometry interaction like for the particle-particle interaction before. After the models we write mesh n meshes followed by the number of meshes 4
and their names. In the next steps, we will define the generation of our particles. First, we describe the particle templates for our two kinds of spherical particles. For the first templates, we set the atom type to 1 and use our variable density as density constant and the variable radius 1 as radius constant. Then we repeat the line for our second radius. With the following fix PDD1, we define the particle distribution. We have to use the number of radii and set our first particle templates PTS1 to the fraction frac1 and the second template to the fraction frac2. Next, we load the geometry for the insertion phase, where the particle will be inserted. After this, we start the insertion of the particle by the command fix ins. The particle should be inserted as a stream using the defined distribution PDD1. For the mass and the mass rate, we use our defined variables from the top. Overlap check yes means that the particles are not allowed to overlap during generation. The command all in yes means that the particle should be generated inside our insertion region. The insertion region is defined by the area of the insertion phase, which is extruded by 0.25 meters. Furthermore, the particles are generated with a constant initial velocity of minus 0.75 meters per second in that direction. Now we express the data for the post-processing. First, we create a new folder named post. In this folder, we will save all data. Then we define a dump step of 0.05 seconds and transform it to dump steps. This means every 0.05 seconds the data will be saved. The following first command line saves the data for all particles every 0.05 seconds to the file particles *lights. It describes information like the ID, the type, the coordinates and velocity will be saved. The other four command lines are used to save our geometry parts. Now we define the run commands of the simulation. In the beginning we run fill steps, which is equal to 5 seconds to fill the silo. In lights, all lines before the first run command will be executed. When the final number of steps of iteration are reached, the lines between the first run and the second run are loaded. After the first run, we use the command unfix ins. This command will stop the insertion, which we named ins before. Now we run settle steps equal to 1 second. After the settling, we define the opening of the lid. We call the fix command move lid. We must use the name of the mesh lid we want to move. The keyword linear means that we want to move it linear in x direction using the velocity value of the variable openVal. Now we activate the next run, open steps. After this, we stop the movement of the lid by the command unfix move lid and start the new run discharge steps to simulate the discharge of the silo for 25 seconds. Now we close the editor and save our simulation. To start lights, we open a terminal and navigate to our folder. Here we type in lights-in and the name of our script, input.lights, and press enter. Now the simulation is running. This will take a while. When the simulation is finished, we start the post-processing by open Paraview. First, we load all files from our post folder. Here we can see the model. Before you go on, check that the view is on 3D. By holding the left bottom of your mouse, you can rotate the model in 3D. If you press the play button on top, the animation starts to run. You can see that the particles are just white points at the moment. Now let's prettify our model a little bit. We select each geometry and change it to solid color. This will appear in gray, which is default. Next we select the particles and set these to V, like velocity. Now the color of the particle represents their velocity. To get volume particles, we select Point Gaussian at the top menu, then we go to Properties on the left menu and set the Gaussian radius to 1. We check the box Use Scalar Array and choose Radius from the drop-down menu. Click Edit below and close. To get a look inside the silo, we change the opacity of the silo geometry. Click on Silo, go to Properties and set the opacity to 0.5. Now we can see the particles inside the silo. Last, we want to create a video of our silo. Click on File and then on Save Animation. Here we can increase the quality of the images and set a frame rate. I set the frame rate equal to 20, which is 1 divided by our dump time, which has been 0.05. Press OK and save the video as AV in our folder. Now the video is created, like you can see on the green bar at the bottom. When the green bar is full, the creation process is finished. Let's go to our folder and open the video. This has been our first silo simulation. If you liked that video and want to see more of this content, please give us a like, leave a comment and visit us under engineerdo.com. Good luck with your DEM simulations!